This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so we can formally start. Good morning, everyone. First, the announcement. We finished the optimization workshop this week, right? And I have announced the due dates and how to submit your reports. They're all in LMS. Next week, we will start with the machine learning workshop. I will post it today or tomorrow, latest. And then the week after is the mid-semester test, which is on April 11th, right? Just 1 hour test on Thursday. It's just 10%, but I think it's good. It gives you a good chance to review the material, especially on optimization, because it will be only topics that we have covered until then. And that week, we don't have any workshops. Then you will continue the machine learning workshop second week after that. Then there is the teaching break, so you will have plenty of time for submitting the report on that. So that's also not stressful. So it will be stretching over a lot of time. Any questions or concerns regarding that? It's all fine, I assume? All right, good. So we have exciting topic today and tomorrow, the constraint optimization. And the constraints are maybe given as functions, but at the end you end up with a set and you optimize over a set, right? So, and therefore we need to talk about the properties of the sets, just like we've been talking about the properties of the objective function that we are optimizing. So, as we have seen, just like the objective function being convex or not convex, the sets can be also convex or not convex. And for the set definition, it is simple. For any 2 points in the set, a set C is convex if any 2 points in the set x1, x2, and any theta between 0 and 1, including 0 and 1, endpoints, then if the interpolation between the straight line interpolation between these 2 points belong to the set, for all x1, x2, then we call that set convex. If this does not hold, then the set is not convex, right? So this one is a convex set. This one is obviously not, because you see when you do this line between the 2 points that I've selected, then these points do not belong to the set anymore, so it cannot be convex. Just one counterexample is enough. So if you find one counterexample, only a set of points for which this, this equation falls outside, then you say, oh, you see, this is the counterexample, it cannot be convex. And this is also not convex, because if you put this point, 1 point here and the other point here, then the interpolation passes through this open part of the boundary, and that's an open boundary. That means the boundary doesn't belong to the set. Therefore, you fall outside the set. Therefore, it cannot be convex. But if it were a nice square with a closed set, all the boundaries belonging to the set, then it would be convex again. Right? And then the definition of a convex hull of a set, that's useful. Like if the set is not convex, we can convexify it by taking the convex combinations of the points, which is defined as this. You choose k points and then combine them with theta 1 to theta k, and then the thetas add up to 1 and they're all positive. So essentially, if you are given these dots, for example, then you end up with a shape that covers the whole thing, because of every line between them falls inside, and then every other thing as well. And then this one, because of the thetas, right? So this will be like a spanning of these basis. They are not basis vectors, but it's a bit like that. It spans the in a limited sense this shape. Or for this one, because you can choose these 2 or any points between, so all of the in-between gaps now belong to the convex hull, so you can create a convex hull out of this non-convex set. So these will be quite useful in some cases when we do constraint optimization. Another thing that I mentioned before, but maybe in next year I will put this slide earlier and make a review, is the hyperplane. And this is quite important as a shape and as a set, hyperplane that divides the space into two parts when you do classification. If you think about it, when you do classification, you also draw a boundary to separate the data into two pieces, right? Binary classification. So, and this will be a linear classifier because the boundary that you draw is a linear one. So the plane is defined by this A transpose X equals B, right? And B being a real number, so this is a dot product essentially, A vector times X vector. How do I know that? Because X is R to the N and A is R to the N. That tells you these are vectors, right? So you can make it even nicer with bold or underline, but many books don't. So that's fine. So that defines actually a line, kind of in 2 dimensions. It defines a line, but we just show it as a line, but in reality it's an n-dimensional. I cannot show it to you, right? So I'm just showing it to you in the lower dimension, and in the 3 dimension it will be a plane, right? So A is actually the normal vector, and then the normal vector multiplied with X gives you the B. So the X will be then any vector, any point on this line, and you can put the normal vector to any x0, that will determine then the B. So that defines the line or the plane and the hyperplane in the n dimensions. And then if you have these inequalities, then it separates the whole space into the Euclidean space, n-dimensional Euclidean space, into 2 halves. A transpose X greater than or equal to B, A transpose X less than or equal to B. And then that may be the classifier, binary classifier you're looking for. Does my data belong to one half space, or does it belong to the other half space? Maybe one half space is the pictures of the dogs, the other half space is the pictures of the cats, and then you're given a picture and your classifier tries to decide whether it's dog or cat. And then the X vector, which represents the picture in this, which makes the future space, and then the hyperplane becomes a linear classifier, linear separator. We will come to that later, but that's the idea. For now, it's just a geometric shape. Right? Have you seen anything with the planes and half spaces in the linear algebra before? Well, now you know. That's the definition. Yeah. The one thing I noticed, it's a very nice cohort this year. We have been very interactive, asking a lot of questions. I'm very happy with that. It made me realize I should have done in the beginning a bit of a refresher on linear algebra and some of these concepts. But it's too late now, so next year I will do that. So because we have gone past the material as we go, so we have done it in an embedded way. Maybe next year I will be a bit more explicit. Because I assumed that you know this stuff and then realized most of the students don't. So that's okay. And I gave you the links to brush up your skills. Right? Multiple books have review material. Appendix of Boyd or the deep learning book has some refresher as well. Another set that we encounter very, very frequently in optimization, constraint optimization, is the polyhedra. The polyhedra, the plural, it's a Greek word, I think, is just a finite number of linear inequalities and equalities. So this is essentially what you see here is, it's just an intersection of multiple half spaces. So you have each of these normal vectors define a half space, and then you just take the intersection of them, right? Intersection of sets. Well, you know that much. I mean, that is something everyone know. You'll end up with a polyhedron, and then there may be also equality constraints. So, in a nice way, as in vector form, this can be written like this, or if you put the vectors as the column vectors of a matrix, as it is done here, then you have this compact representation. With X belonging to R to the N here, that is implied. So all those X for which this curly bracket means element by element, less than or equal to B, rather than the, that means element by element. the other one is normal inequality. This is element by element inequality. Then this notation is from Boyd's book. So as I mentioned, if two sets are convex, their intersection is convex too. You can check the again basic mathematic material for that. That's kind of intuitive. And then maybe some less intuitive is if you take a convex set and do an affine transform, linear transform, then it also preserves convexity. There are many other operations. I refer to Boyd's book for many other operations that preserve convexity. A lot of detail there. I don't want to go that much into geometry and this convexity business. But the important thing is, yeah, if I have two convex sets, intersection set is also convex. That is something important to know. Just let me show you what I mean by that, and then I can, as a note. There we are. It's good. So, right, and that's very intuitive. So if I have a convex set and another convex set, I intersect. You see, the intersection is also convex. And intuitively, convex set union with a convex set, would it be convex? Not necessarily, right? So there may be special cases, but not in general. Just like you see here, if maybe I draw it a bit more exaggerated way. So if I have a convex set and another convex set, they intersect, right? So the union would be then this big red set. But if I take 2 points, obviously, right, and then draw a line, this part is falling outside, so it is not necessarily convex. So, but intersection convex is convex. Good. Another thing that's not in the slides, maybe I should have included, but now I can do it in the whiteboard, is this very fundamental idea that's it should be in the books, but somehow it's not prominently mentioned. If I do an optimization, if I solve an optimization problem, right, a constraint optimization problem, let's say I want to find the peak of this mountain, right? Bear with my bad drawing, right? Okay. There is an unconstrained case, so let's say this is my unconstrained x star, the peak of the mountain. If I put a constraint to the picture, right? So this is the domain. There is a plane, and then there's the mountain on top of the plane. Does that make kind of sense? Yeah. So if I put a constraint, so let's say I have a constraint that looks like this, right? So then suddenly my solution will be, the blue solution will be, let's say this one, projection up. So the constraint solution is x star, right? Because it's in the constraint set. It has to be in the slope. If this is not in that set and this is in the set, then it has to be in the boundary, right? So I should actually put this to the boundary. So that's the boundary, and then that's my mountain. Oops. Right. So inverted ball, okay? And then the other one is not, because it's outside the constraint set. This is the unconstrained optimum. So actually these are the f. This is f of x star, and this is f of x constraint and unconstrained star. So this is x unconstrained, and then this would be then the x constraint star. Make sense? Everybody with me? Yep. So there is a simple theorem. It says if I choose let's say I choose even a smaller set. What if I choose this one? Then the solution will be this, right? xc2 star. And then that will be fx star c2. Okay? So I will end up with the third point. The fundamental theorem says I cannot do worse by increasing my constraint set. So, in an optimization problem, I cannot do worse by increasing the constraint set. So, or I should be do at least as good as the previous version, right? The corollary is that. So maybe we can write it as if constraint 1 is a subset of constraint 2, or C2 is a superset of constraint 1 set, then f of x star in C2 will be greater than or equal to f of x star in C1 for max x star in C1 or 2 f of x, right? F of maximum x in C, right? So that would be the idea. So if I increase my search space, I shouldn't do worse by that. It is kind of important. So the best solution will be then the unconstrained case. Then any constraint you bring may or may not decrease the solution. It's an inequality. If the peak of the unconstrained is already inside your constraint set, then there's no problem. You will get the same result. But as you constrain more and more, there's a distinct possibility that you will do worse, because you may, the peak may fall outside your constraint set and you're in the slope. And if you constrain even more, you go even down in the slope, possibly, right, with an inequality. Does this make sense? This is a very important connection. And it's a very fundamental theorem. And it pops up very invisible ways everywhere. Like, if you extend your search space, you cannot do worse. So it has a lot of real-life implications. So let's go to this geometry of the stuff. So the first question here talks about that. Which of the following sets are convex? And I haven't gone into detail. Actually, this question has more parts in Boyd's. I think I took it from Boyd's book. And doing this, I think, will give us kind of a more feeling of these different shapes and, polyhedron and the half spaces. So let's go talk about that. Okay. So which of the following sets are convex? So we start with a slab, and then you may ask, what is a slab? And if you know mathematics, you don't need to care, because what is a slab is defined here, right? The slab is apparently this. So x in an n-dimensional space. So this is a general definition for which the A transpose x is between is less than or equal to beta and then greater than or equal to alpha. So all you need is actually to know is the definition of a half space and hyperplane, because A transpose x equals B is a hyperplane, and greater than or equal to, less than or equal to defines hyperplane. So essentially, we have an A transpose x, and then A transpose x less than or equal to beta equals beta will be done this, and then A transpose x equals alpha will be this. Why are they parallel? Because they have the same normal vector, right? A is the same, right? This is A, this is A. You can put the normal vector anywhere you like. And then one of them says, oh, it is less than or equal to beta, then that would be this side. And the other one says A transpose x is greater than or equal to alpha, that would be this side. And then you get this big space in between, right? And that would be a slab then. Is this convex? Yes. Yeah. I mean, you can mathematically prove as well, but intuitively it is convex, yes. Good. So you see this half space thing is once you get used to it, it's pretty straightforward. A rectangle of the form, again, this is a hyperrectangle because it's in n-dimensional space, is of the form. Is it convex or not? So that will be then yeah, it is like a rectangle. We show it in, I'm showing it in 2 dimensions, but obviously n-dimensional version will be that. So this is actually an intersection of 2 slabs, right? So, or you can think of intersection of 1, 2, how do I show this? So let's do it this way, yeah. So 1, 2, and then 3, and 4. Intersection of 4 half spaces, because x is less than or equal to, xi is less than or equal to beta I, right? And alpha in each dimension, x1 is less than or equal to alpha 1, less than or equal to beta 1. In this dimension, x2 is less than or equal to alpha 2, less than or equal to beta 2. And then you can imagine it goes to n dimensions, and they are all intersections. So all these, when all these things intersect, each of them is again a slab in 1 dimension, and then the intersection of these convex slabs, so is again convex. So this is maybe just to say slab is intersection of half spaces, and then intersection of convex. Therefore, it is convex. The same way, intersection of slabs, which are convex, therefore it is, yes, it is convex. Make sense? Yep. Also, it gives you a feeling what possible shapes are there. Now, there is another shape. Yeah, I'm not giving you for you to memorize these shapes, right? I mean, you will have also notes for the exams and so on, and this is all in Boyd's book and somewhere else. I just want to, get used to this stuff a little bit. A wedge. Okay, you may say, what is a wedge? And then you don't need to, that's given here. So that's the beauty of mathematics. It's language independent. So a wedge is a set of x, each in n-dimensional Euclidean space, r to the n, real numbers, such that, okay, I have A1 transpose x less than or equal to B1, and then I have A2 transpose x less than or equal to B2. So I have 2 half spaces, but now A's are different, right? So then the A1 may not be the same as A2. So that means, okay, I will have then some A1, and then that will be like that, and another A2, and if they are not the same, then they need to intersect somewhere, right? You can imagine if they are not the same, so I will have done some A2, and then less than or equal to, A2 transpose x less than or equal to B, so these are 2 half spaces, so they will somewhere intersect, and then the now kind of wedge starts to make sense. It looks like a wedge, like a slice of a cake, in a sense. So, and then, is it convex? Because, yeah, it is it's a convex set because intersection of 2 half spaces. So, which are convex. Therefore, intersection of convex is convex. Actually, there is a special case. This is called a cone. It's a cone, as a side note. If B1 equals B2 equals 0. So in that case, it becomes a cone. So that's another definition. And then the D, so we say yes here. And let's do the D. The set of points closer to a given point than a given set. So this has implications when we do some classification business, right? How does classification come into the picture later? When you have data points, they will be living in the space, and then classification is about separating the data points to, binary case, 2 classes or 3 classes and so on, right? So when we do the space business, this is the space where our real data points vectors live. And the picture can be a vector, and anything can be, a vector. That's the digital world. So set of points closer to a given point than a given set. So how would you say this mathematically? you choose a point x0 and say Euclidean distance, right, norm, square root, second norm, L2 norm, x such that, you know, again, r to the n, x is close, this distance of x close of x to x0, so let me put an x0 here. So I look for points that are, their distance to x0 is less than or equal to x distance to y for a set y, right? So it can be a non-convex set, so let me draw a general y set, set S, and then the points y are here, right? Any point y. So then the distance of points, the points that are closer to x0, that means, that means actually I need to find the closest y's, like maybe these and these, right? And then it will be like a bit of like the Voronoi stuff. So this will be then this, and then this will be then this. Any of these are farther away. So this will also draw something like that, right? And just like we were saying in the other one, so all these points here will be closer to x0, and the others will be, you know, there may be multiple points, then you need to do all that intersections. And then that will be, but you see that will be then some set of points will define the intersection. So formally, we can write the intersection as x such that for the intersection of all the y's, some of the half spaces, if you choose this one, for example, that also defines a half space, but it will be here. When you intersect, the other one takes precedence or is more dominant. So it will be then x such that x minus x0 distance, as we defined, is less than or equal to x minus y distance, right? Or if you square it, it will be the same. Distance square will be also the same thing. So, and then if you intersect for all points in, you know, you can do an infinite intersection in mathematics. It's not possible computationally, but mathematically well defined. So it is, this is a convex set because it's a half plane, and then each of them defines a half plane. And again, this is an infinite intersection of half planes. Convex intersected convex is convex. So it is, the answer is again yes. So these are all nice convex sets. I mentioned why convex sets are important. The convex optimization is defined through convex functions, convex objective functions on convex constraint sets. Right? You call a optimization problem convex optimization problem only if the objective function is convex and the constraint set is convex. So I think we should also write this in our notes. It's worth writing down to the whiteboard, virtual whiteboard. So we call an optimization problem. I think I will make slides of these next year. Convex. So it is important. The optimization problem is convex if a objective function is convex, which should use the objective functional convexity, right? And the constraint set. I mean, if there is a constraint set, if it is not, then it's also, the whole space is fine. That is convex. Or unconstrained. Then that's also okay. Right? From engineering, okay, mathematicians love this set business, you know, closed set, open set, blah, 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 right? I mean, okay, there is the whole, half of mathematics is about these edge cases. From an engineering point of view, you know, in my opinion, take it or leave it, most of the problem you encounter, there is a constraint. You can put a big box around it. You can make a hyper box, right? And then say, my problem lives in that box. So the thing is, life is constrained, But most of the time, if the box is too big, you don't have to care. So in engineering, you always encounter some constraint problems. And then practically, sometimes those constraints are so far away, you don't have to care about them. Then you fall back to the easier world of unconstrained optimization. Right? So practically, some problems are unconstrained. You model them as unconstrained because the constraints are, your box is too big and the constraints are too far away. Sometimes, of course, you have real constraints. Most of the engineering problems, epsilon doesn't matter. Right? When you have a circuit, your transistors, your resistors are plus minus 5. Whether the set is closed or not doesn't, what does it even mean in that case? So you don't have to worry about the set being closed or not. So you can always look at the closed sets. So those edge cases are not important. So you have nice sets at least, even if they are not convex. They are kind of closed sets. You don't have to worry about all this mathematical stuff that talks about, what happens when you're epsilon away and so on. And believe me, a lot of stuff is about that. So that's quite irrelevant to most of the time to engineering problems. Anyway, so that's the thing. That's the definition. And let's go back to our slides. Do we have another problem no. So we come to the now heart of the matter, right? You must have all heard the Lagrange multiplier business sometime. In your life, even though you haven't taken optimization, I assume. Is that who has heard of Lagrange multipliers? Who hasn't heard of Lagrange multipliers at all? All right. Okay. So now we will learn formally. All right. We will start again to make life simpler. We will start with equality constraints first. And then I will add the inequality constraints later. So equality constraints are of the form. You may have multiple equality constraints, like h1 of x, h2 of x, hm of x. Just to refresh your memory, the canonical form of an optimization problem, remember, looks like this. So you have an objective function, then maybe a set of inequality constraints defined by these functions. And then you have set of equality constraints by these functions, defined by these functions. Of course, these constraints, equality and inequality constraints, create your intersection of these inequalities and equalities gives you your constraint set. And then if that set is convex, then it's a convex optimization problem. But most of the time, constraints are dictated by these equations, not by, often nobody gives you a shape. The shape is defined by the, just like we did in the example, through the, equations. And then we will start to make our life easier, believe me, with the equality constraints. Because that's the kind of educationally, that's the right way to go. So when you have a bunch of equality constraints, they define, let's say in 2 dimensions, h of x may define a line. So this is the line on which you need to optimize things. Your kind of optimization objective has to be, your optimal point needs to be somewhere on this line, for example, or curve. I'm sorry, it's a curve, right? It's not a line. Now, in the n-dimensional space, you can imagine this constraint set is defined by multiple equalities. Okay, are you with me? Good. So let's say I have a point x star. Any point, right? A point, x star. And I can actually draw a tangent plane to this x star, right? How do I do that? Actually, I can use the gradient of the constraints, not the gradient of the objective. Gradient of the constraints at x star will be a vector like this. And then if I use this vector as the normal vector of the tangent plane or tangent line, then that defines this tangent line or tangent plane here. So you see here, this is the 2-dimensional representation, this is the 3-dimensional representation. And as human beings, we cannot do the 4-dimensional representation. It's beyond our capability, right? So if this is your surface determined by the set of equality constraints, then at any point, x star, I can actually define a tangent plane by using that gradient of the constraints. Again, not gradient of the objective. Then that will make me define this tangent plane or tangent hyperplane if you do it in n dimensions. If it's two-dimensional, tangent plane is one less, it's line. If it's three-dimensional, tangent plane is a plane, two-dimensional object. If it's an n-dimensional constraint set, then your hyperplane will be n minus one dimensional. In the fourth dimension, then your hyperplane will be three-dimensional. Things become pretty difficult to visualize. But mathematically, its definition is pretty straightforward. M is then y, all the y, such that, you see this is another way of doing such that. Different books do in different way. So the set of y in R to the n, such that the gradient of h at x star, okay, that's the key point. I'm just defining it at that point, the tangent of that point, with respect to the constraints, times y, the dot product should be 0. All right? So dot product will be then scalar. The 0 is actually, it is said in bold, but it is actually one-dimensional. A point satisfying the constraints, so any point satisfying the constraints is this. It needs to satisfy the constraints. Any point not satisfying one of them will be outside your constraint set, obviously. It is said to be a regular point of the constraint set if the gradient vectors, if you take this is a gradient, it's a vector, so these are the, with respect to each dimension, with respect to each constraint, h1, h2 to hm, if they are linearly independent. So that is a regularity condition. And then at a regular point, then the surface, which will be then the tangent plane, defined in general, that hyperplane we can a regular point of the surface S, surface S in this case will be the constraint set, right? That will be the surface S. So let's in this case, this is S, and yeah, this is S, right? Okay, a regular point of the surface, which is the constraint, right, set, defined by this, obviously, yeah, what it's meant by the surface again, you don't even need the language, you can just look at the math and it says the surface is defined by the constraints, that means it's the same thing as constraint set. The tangent plane at that point, at any point, is then defined by this. So, but this is the standard definition of a hyperplane. So this is a tangent plane. All right, so you will say, well, what does it have to do with the whole story, right? I'm actually giving you a geometric interpretation of what the Lagrange multipliers is. So now, we know that. Now we combine this with this idea. So I can do this at any point. Now, if I have a set like this, x, this is the same as the surface, right? Okay? But with inequality, it is shown in an inequality sense because it's hard to also show it with a little bit with the equalities. Let's call it, this surface S. Equality constraints, then the constraint set will be done this, right? Yeah, actually, this is the visualization is getting messed up, right? Because in the three-dimensional space, four-dimensional space, it will be a whole three-dimensional surface. So what is inside, what is outside gets a bit blurry. But bear with me. So I have a constraint set that that I impose on my optimization problem. And if this is my objective function and I'm trying to minimize, right? Then the global minimum is somewhere here. But with respect to my constraint set, this will be my optimal solution, right? You see that? So let me delete this thing. So this would be then the optimal solution because of the imposed constraint. And then assume that x is imposed by the equality constraints. So that is then h of x equals 0, right? Defined by. And this is my x. Now, obviously at that point I will have a gradient, right? And then the gradient will point towards the gradient is the gradient of the objective function, f0. Good. So, but notice at the same time that x is also on the surface, right? It is on the surface because it is satisfying the equality constraints. And I can actually draw a hyperplane at that surface, at that point, at that very specific point, right? I can draw a tangent plane at any point of the constraint set, but that is my solution, and at that solution, I also can put a hyperplane. You're with me? And that is this guy in 2 dimensions. This is the same thing as this tangent plane, right? So then that would be the x star would be then the extremum point, minimum or maximum, depending on your problem. So when we combine these two things, we observe something interesting. At a regular extremum point, x star on the boundary, right? The point is on the boundary, therefore it automatically has to satisfy the constraints equations. Yeah, because it has to be, it's a constraint optimization problem. The normal of the tangent plane, yeah, that is this guy. And the gradient of the objective function, if the gradient of the objective function at that point points somewhere else, then you would move in that direction, right? And then find another point, and that would be your optimum. Because if you're at the optimum, if this is very simple. So I want to climb the mountain. My nose shows, towards the mountain top, gradient. And then there's the boundary. I hit the boundary. You see, I cannot move anymore. If I didn't hit with that angle, I could have moved a little bit on the boundary, come to a point, and again I point up and I hit the wall, right? The wall is like, if it's a curve, every tangent will be like the wall when I hit there. So the closest point to the top puts a tangent wall in front of my nose, so I cannot move anymore. You see? So that's why, that gradient and then the tangent plane's normal, they are perfectly aligned. You don't see this? I thought this would be nice explanation. Yes?
What's the point of the tangent plane?
Sorry?
What's the purpose of the tangent?
The tangent plane is on my constraint set. When I hit the solution, the tangent plane is the tangent constraint, that I counter, the tangent wall that I counter on that surface.
But why would we care about that when we know that the local minimum is still the same point?
Yeah, at that minimum point, the tangent plane and the gradient are aligned. The wall in front of me at that point, right? I hit the boundary. I cannot move further. There is a tangent wall in front of me. You agree? Yeah, but the tangent is now my constraint at that point. It's a local approximation, first order approximation to that constraint curve. So that is really literally a wall in front of me. And I'm pointing towards the gradient, and that wall is in front of me. But the walls is defined by its normal, then the normal will be also pointed, in parallel to the gradient. Make sense? Yeah, okay, he understood it, then he will tell you after the class. So, I'm joking. So if they are perfectly aligned, this is the lemma. Let's look at it mathematically. Then if I have this, all the y satisfying, the tangent plane must, at x star, then x star is a regular point of the constraints, and a local extremum point, a minimum maximum of f subject to these constraints, is defined. Then for all y satisfying this, so that is the tangent plane points, must also satisfy at that point, the tangent to the gradient is the same as tangent to the, to the constraint set's normal. Therefore, if they are aligned, you can actually put a linear relationship between them, kind of write it as gradient f at x star is equals to some lambda times gradient h at x star. That's actually this equation. And if you bring the lambda back, lambda is any r, or e to the m, so that's an Euclidean space. It belongs to the Euclidean space. If they are aligned, I can write one in terms of the other, and then that will be very much the case. So essentially, gradient f at x star at that point is lambda minus lambda times gradient h at x star. Right? One is the multiple of the other, and lambda is a scalar. Lambda is not a, I mean, these are the vectors, so then if they are aligned, you can actually, each of them, if you do this for each dimension, then you have a lambda for each dimension, so you end up with a with an equation like this. So these are then these constraints, the connection between the two are called Lagrange multipliers. So actually, we end up with an object called Lagrangian that is defined as, we have the objective plus these lambdas, because of this, if it's a regular point, lambdas times the equality constraints, and lambdas can be plus or minus. So therefore, the moving to the left-hand side and right-hand side didn't make any difference. So f of x is a scalar valued function, plus lambda is a vector, so this is a dot product with the h. If you have only one constraint, then it's scalar, lambda 1 times h1, or if you have multiple, then you need one lambda for each constraint to get that alignment. So if you write the Lagrangian like this, then first order conditions, now if it's a constraint optimization problem, intuitively you can guess I need to take the constraints into account when I solve it. In an unconstrained case, we were just taking the gradient of the objective function. Whereas here, we need to take the gradient of the objective function, and we need to also take into account somehow the constraints. Therefore, we need to operate everything with the Lagrangian. So now we take the gradient of the Lagrangian with respect to x. And if we take the gradient of the Lagrangian with respect to lambda, that's actually pretty straightforward. You end up with the constraint. So this is constraint, the original given constraints, and this is the counterpart of the first order necessary conditions for the unconstrained case. So Lagrange himself actually didn't give this geometric one when he wrote back then in 18th century. He actually was thinking purely in algebraic terms. So he was saying, I need to then put a Lagrange multiplier and add those to the objective, then create this Lagrangian function, and then work with that Lagrangian function. And algebraically, without any geometric interpretation, one can show that leads to the solution of the problem. But I thought, this whole story about the story about the individual, the alignment between the tangent planes, and then therefore the alignment of their normals of the tangent planes gives you the kind of an intuition of what is going on. So let's solve a problem to do the mechanics of it, so you get used to it, and then we get a couple of problems, and then we go back a little bit to the second order necessary conditions, and then the intuition. So this is a kind of a straightforward one, but it's a very nice question. So it is a question: construct a cardboard box of maximum volume given a fixed area of cardboard. So it's like a primary school problem. You are given a cardboard box, a piece of paper, and then of certain dimensions. The dimensions of the box is x, y, z, and the total area of the cardboard is c given. Then we want to create the biggest box we can do, right? So that's a very nice activity for primary school kids. But now we are grown up, we can actually use the optimization theory to model this and find the solution. So first of all, what are we trying to do? What is our objective? This is actually really nice, so let's do it together. So what is my decision function? X, Y, Z, right? So x1, x2, x3, it's a vector. So it's like when we were working with the vectors, we could have called it, I don't know, maybe alpha, would be then x, y, z. But let's keep it, you know, simple with the x, y, z. So we want to decide on x, y, z. But then what are we trying to do? What's our objective? Volume, right? So, and then what is the volume? Volume is actually multiplication of these three because it's a box. In hyperplane, it will be then hyper rectangle or something. Yeah, it would be hyper rectangle, right? Based on the definition we discussed. All right, I'm trying to maximize. So then I can write the first part. Maximize x, y, z, which are x, y, z are scalars. They are r to the plus actually. They are greater than 0. Of volume of x, y, z, which is x times y times z. Good. So I know what I'm deciding on, and I know what I'm trying to maximize. Good. But then, is it a constraint problem? Yes. Right? So we need to put the constraint such that, subject to, not such that, subject to, that's also the same ST. So what is the constraint? The constraint is the area constraint. So it basically means 2 times xy plus 2 times xz plus 2 times yz, right, equals C, the area of my cardboard. So we have the no, this it is a closed box. Why do you say that? It's a closed box. Like this one has one side each, right? So the top part is, let's say, x, y, right? So that will have 2 of these. Yeah, you have a closed box. It's a closed box. What am I missing here? So two of these, and then 2 of these, right? Okay, picture is wrong, okay. Thank you. Yeah, excellent. Careful guys. Right? Yeah. Okay, so I see you're extremely good, careful, but then take this one, all right? Okay, so the end box will look like this, so forget about this, all right? I'll update the picture. I even drawn myself. I took it, I wasn't careful about it. Excellent. So, but you believe that it's a closed box, then the area will be this, right? Area of a box is this. So subject to area constraint, area equals C. All right, so forget about this, huh? Okay, excellent. So now we need to solve this. All right. How do we solve this? We write the Lagrangian, because this is a single equality constraint, right? So we write the Lagrangian, which is the objective, x plus xyz, not x plus yz, xyz plus, we can write it in this way, lambda, there is only single constraint, so there is a single lambda, times, if I write it this way, xy plus xz plus yz minus c over 2. Right? I can divide the two. Okay, so that will be my Lagrangian function in terms of x L. Actually, L is in terms of x, y, z, lambda, right? The decision variables and lambda added. Now I have an additional variable in L. Then I can write the first order condition. So taking the gradient of the derivative of L with respect to x will be then yz plus lambda times this c over 2 doesn't matter here, interestingly, so you get the lambda y plus z. And similarly, I can write del L, del y, it will be then xz plus lambda x plus z and then equals 0, the first order necessary conditions. And then z will be then xy plus lambda x plus y equals 0. All right? Good. And then what I have, in addition to these, I need to then take the derivative of this with respect to lambda, but that will give me simply the condition, xy plus the constraint itself, plus yz minus c over 2 equals 0. All right? So I write the first order conditions with respect to all of the decision variables and then the lambda. Then we solve this set of equations. Right? It's kind of an easy trick for these. If we multiply this by x and let me use a different color. If I multiply this with x and this with y and this with z, then I bring it to the similar form, and then I can subtract them. So for these two, for example, I get then x, y, z plus lambda x, y plus z equals 0, and then x, y, z plus lambda y, x plus z equals 0. Right? And if I subtract the two, what do I get? I get lambda. Lambda z's also cancel out. X, y, z's cancel out. I get lambda x, y's cancel out. X, z's and y, z's remain. So z is here, and then it will be then x minus y equals 0. So that means y equals x. And if you do in pairs, you get x equals y, y equals z, then x equals z. So you get they are all equal. So we get actually x equals y equals z. So it's a cube. Right? Then the final thing is I need to put it to the area constraint. So if I have that, so I have got all of them are equal, so I can call them, I don't know, beta square, 3 times beta square, 6 times beta square equals c. So then beta, which is the side, let me call this equal to beta. Yeah, I love this virtual thing because I always, in the physical blackboard, I always run out of space. I used to. Then you get the c over 6 square root, one side. So it's a cube. With beta as sides. All right? So, whatever. You see, this is very algebraic. Like the whole geometric interpretation is nice and so on, but how you use the Lagrangian is very algebraic. So you write the Lagrangian as a lambda plus the equality constraint, then you just apply the first order necessary condition, go back to the unconstraint, you were taking the derivative gradient of the objective function and equating to the 0 or derivative equal to the 0. Now you take the derivative of the Lagrangian, but because Lagrangian is function also of the lambda, this Lagrange multiplier, you also take the derivative with respect to the Lagrange multiplier, but derivative with respect to the Lagrange multiplier is nothing but the original constraint. So you have one more equation, but that's the original constraint in addition to the first order conditions. And when you put them together, you solve it. By the way, when you take the so this the problem is kind of bilinear. Therefore, maximizing this, the first order conditions are sufficient for maximizing this because it's a linear as a linear multiplication of the decision variables. So we need to be still careful about convexity concavity. In this case, that's a nonlinearity, but obviously you increase x and y and z, they are all positive. We haven't kind of made it explicit here, we kept it simple. Then you hit the boundary, and then at the boundary solution, of course, your cube is bounded by, what I mean boundary is, in this case, the boundary is the cube's area, all of the area you use. So what will be the boundary in this case? To create the biggest volume cube, you have an area of carton given, like the paper given, and then you are using all of it that you are given to make as big a box as possible. But that's also intuitively meaningful, right? So you wouldn't use less than what you are given because you are trying to maximize your box. So in that sense, you hit the boundary. You use the all of it that's given, but it's also given as an equality constraint. I didn't give it as an inequality constraint. I could have told you, use less. You can use less than the area, the paper you are given. That would be an equality constraint. But we intuitively already know that we will use all of it, so it's better to write it as an equality constraint. I will come to this hopefully today. So let's give it a break of 9 minutes at 11:15. We continue. Right? With another question that is relevant. Okay. I should mute this. And I shouldn't write on this because it gets to the recording if I write on this.
Oh, okay, that's fine.
it would confuse everyone. Last time I wasn't very careful with that.
I just had a couple of quick questions. So what did you actually do from here to here? How did you?
I multiplied them with x.
Oh, you just multiplied them? Oh, I thought you were taking it with at the point x. Oh,
I think I can write this much. I'm just multiplying them with x. Yep.
X, Y, Z. Okay.
Yeah. And then the rest is quite straightforward.
Yeah, I understand the rest then. With your wedge one here, like these, I don't understand why you can suddenly decide which side of the line you're going to take as the half plane. Like, wouldn't this actually more be correct to say that it should be more like this, but these are the actual half planes here? So when you combine them, because they're both less than equal to B. Like, I don't understand why you can just suddenly choose the direction.
Actually, yeah, that's what the question gave. I think they should give a little bit more on that. You're right.
So it's actually not a convex set.
No,
or it is.
In that case, it's still convex. It
will be still convex, but I think that's
maybe that's a more general case of the wedge, right? I mean, when they say wedge, collegial shape that we always think is, and the mathematical definition.
Yeah.
I don't know. I'm just operating.
Yeah.
They call this wedge. This is the shape, and you're right, but it's still convex.
Okay.
And it still intersects.
Yep. I agree that it's still convex. I was just curious, like.
Yeah,
why? How does
it will be still like a it will be still like a wedge, right?
Yeah. Yeah, it's just like a obtuse wedge. I
haven't thought of it, to be honest, but let's think about it together. So if what you say happens, this will be this, then this will be this.
Yeah.
So I'm ending up with this guy. Yeah, that's a wedge too. Maybe that's why they call it wedge.
Yeah, I was just like.
Yeah, that works too, right? That would be a wedge too.
Yeah.
All right.
If it's a unison, yeah.
Yeah. Well, intersection will be still a wedge.
And
that's why I guess they keep general.
I asked a question about the plane. Now, I understand how to get it and what it is, but why does it matter? Because why does it matter what the plane is when you're always going to be bounded by your constraints here? Like you're never.
Yeah, but
gonna...
that's your tangent plane there.
Yeah, but why do we need that?
But that tangent plane, like that creates your Lagrange multiplier. There's another way of justifying the Lagrange multiplier.
So where's the tangent plane on the Lagrange multiplier here? Like where
this is the tangent plane's normal.
Okay, right. I didn't understand that. Yeah.
Well, then why? Like that's the tangent plane's normal. It's in the slides, right?
Yeah.
So that's the tangent plane, and this is your gradient.
Yeah. Okay.
Yeah. I mean, also all this stuff, H, you know.
Yeah, this is the gradient of the space, right? Yeah. Okay.
Do you mean that we just use the tangent plane to find the normal of the function?
Yeah, they are aligned. They are aligned. So this is kind of a nice way of giving an intuition on the thing, I guess.
And what exactly does this multiplier do? What's the constant?
These are the Lagrange multipliers.
So how does that change this geometry here?
It's not about geometry. I'm just trying to justify the Lagrange multipliers. You actually algebraically just write it like this.
Okay.
You write this is the Lagrangian, and there's a lambda.
Just because.
And then Laplace did it, it's algebraically, it solves the whole thing.
Yeah, okay.
But then then people will say, okay, well, what does it mean? One intuition is I'm taking into account the constraints.
Right.
But then why do we do these? Why is it this form? Why this linear form? And that explains it a bit in a geometric way.
Okay. All right.
There is much more deeper interpretations of this whole thing, but mechanically it's very simple. Yeah, you just write the Lagrangian and take the derivatives, and that's. But then this kind of gives a geometric intuition to that.
But I don't understand where this factor comes into the geometric intuition yet.
Yeah, but this is the geometric intuition that I explained. That is the geometric intuition.
Yeah, but it's not related to this at all.
What do you mean?
This multiplier, where does that?
Yeah, but it is coming in this optimization. If that is your set of constraints, and then you have a gradient at that point, and if that point is your extremum point, optimum point, then gradient looks that way, and the other gradient looks that way too. So they are aligned at that solution. So this allows you to find the solution. That's why you have a lambda star.
Right. Okay.
You have a Lagrange multiplier that solves the.
Yeah, so it's still something that you minimize or maximize all
Yeah.
Okay. Right.
So for the solution, you find not only x but also the Lagrange multiplier.
Yeah.
It will become. I should mention it. This is a good question. So you solve for the. Here you solve it, but then you also find the. Here it doesn't show up the way we solved it, but in other cases you find the Lagrange multiplier as well. We will have examples of that. Yeah.
I understand how, that we have.
This is just also regularity condition. It will show up.
All right, thank you.
Yes, so just one more question. That's about if Q is a positive definite, for example, is and then the function should be.
It's like a ball shape, yeah.
Yes. So how can we search for the maximum? Should it be the minimum of the function?
Yeah, that's true, because when I did it at home,
I should be negative definite. Didn't anyone say that?
Because when I tried to do it myself,
My demonstrators were supposed to tell me, catch this mistake. Oh, damn it. It should be negative definite then.
Negative definite.
Right.
Okay. Negative definite.
Yeah, it should be negative definite or you minimize.
Okay.
I'll send an email today.
Okay.
But
thank you.
You're right. So I'm. All of them are sleeping, I think, the demonstrators.
Professor, my question is, what is gradient of hx? Because we have so many.
But at that point, this is the x star.
X star.
Yeah, that's x star.
Yeah, I know that it's x star, but like.
This is gradient. This is the derivative of the constraints.
Yeah, but I will say the gradient of first one is delta h1 x, right? And is it vector or a matrix? Because they have so many gradient of different constraints. Right? So it's like we have m constraints, and each of them have each gradient. And for this one, it don't seems like it's a matrix. It's a vector. I see.
It's a matrix. Then you multiply with the Lagrange multiplier. I'll mention it now.
Okay.
That's a good point. Yeah, that's a very good point. Thanks for that. Actually, that's a very good point. I should mention that. There's these two things to mention. I have to continue back. Like, let's talk about after the lecture.
我就问一下，这个刚才是报升矩阵，它是一个 vector，但是像第一个，如果它是一个就是普遍的话，它有它一个自己的一个形。如果但它每个都是 vector， 这每个都是 vector。
May I ask the gradient? The gradient is like.
Yeah, but then this is a gradient. This is a matrix actually. I should say that.
This should be vector
No, it's a matrix
matrix.
because each column will be a vector.
Yeah, each column is.
Okay, so not this.
I will say it now. I will say it now.
One question, very quick. So the gradient is this vector, is this one. This is gradient or this is gradient. I mean,
It's still a tangent plane.
okay, so for example, this one, the gradient is this line or this line.
The gradient is the vector.
The vector, this
Yeah,
line.
this is the vector.
So this is the tangent plane.
Yeah.
Oh, okay, thank you.
Yeah, but that's what I say. Tangent plane next to that line. Straight line is the tangent plane. Straight line is the
Yeah,
tangent.
this is tangent plane.
Yep. All right. Back to work. This is working. Good. Recording continuing. Hey, miracle. One note to here. Actually, I was just scratching my head on that and myself, and then I should make it clear. So when you take the point and you have multiple, this is a most general notation. That's why it's a bit cumbersome. If you have this notation, if you have m constraints and x is multidimensional, right? So actually, when you take the gradient with respect to each constraint, each scalar constraint, you end up with a gradient, right? So this is actually a matrix. So I took this from Lundberger's book, and it is not immediately obvious that it's a matrix, equality here that defines the tangent plane. So this is a matrix that has as the columns, you have these individual gradients as the columns, and then that's multiplied with a y, that is actually r to the n, and then you get a zero. Actually, I was saying this is a zero of a vector, so it would be gradient 1 h1 to ... transpose, and then you have the y1 to yn, and then you have equals 0, 0, 0. So that would be the right one. That's why also when you write it this way, this is a vector, this is a vector, this is this matrix, then matrix times vector will be then vector, vector equals vector, then again 0 vector, right? 0 is bold here. So that's the that's the more general notation here. That I should have been a bit more careful. But now it's a bit clearer. So the Lagrange multiplier is like that. Good. And then I think that was it, right? So there was another thing that I wanted to say. Well, okay, we go to this question. Again, this is kind of this is actually a modeling question. So and it's relevant to the workshops. So if you have a network, I need to also make there is a typo apparently in the workshop that the positive definite, negative definite, or max minus min. So you need to find the bottom of the ball or peak of the ball. The way it's written, I think, is Q is positive definite, but I ask you to find the maximum, then you will end up with the one of the boundaries, right? So that wasn't the intention. I was actually asking a simpler question. So in the workshop, I will send an announcement on that. So let's look at this problem. This actually is a quite popular problem. We give a network of n nodes with directed links connecting each pair of nodes, and then variables are the flows. Xij denotes the flow from node I to node j. and the cost of the flow from I to j is given by Cij Xij. So x, we have the nodes I, I, and then j's, all the nodes, and then in this graph it's A, B, C, and so on, but they can be x, and then actually the x's are the flows between the nodes, and then Cij are the constant costs. So if there is a flowing network with some flows through the network, then the total cost will be then the sum over Ij and the Cij Xij over each link flows, right? And then the question says, by the way, these link flows are lower bounded by Lij for link Ij between the nodes Ij, and then upper bounded by the Uij, between the nodes Ij. And if there is an external supply I at a given at a node I, then it's Bi positive. Then there is an external flow entering, and then if it is Bi is less than 0, then the flow exits the network. I'm just keeping it, by the way, very, very abstract, right? Whatever the flow. And then we can assume that the sum of the BIs equals 0. This is one way of writing 1 transpose. 1 is the bold is the vector of ones, just like the 0 was the vector of zeros, times B. That will just be the sum of BI equals 0. I like actually that notation better. All right, not this one. This is a bit, shorthand, but it's kind of fancy. So we have the conservation of flow, total flow into a node I, all the flow that passes through a node and the input node and exit, they should add up. So the amount of flow, the things that flow don't disappear out of thin air. They enter, exit, and go to the neighbors or come from the neighbors, but nothing disappears. There's a conservation of flow. All right? The problem is to minimize, okay, now this is the setup, right? It introduces the variables and so on. The problem is to minimize the total cost of flow through the network. So this is our cost function. So our subject to the constraints described above. Formulate this problem as a linear program. Actually, just formulate this problem and then we can observe that it's a linear program. Right? What is the decision variable here? We decide on the flows. X is the decision variable. Xij's. Okay, now make it a bit more concrete. This could be a power system, electrical power system. Then you have the currents flowing through the power system. The current electrons don't disappear. The generator may pump, current. You consume, or it could be the power. Power itself, real reactive power. Real and reactive power flows through the network, and then transmission lines have a cost when it passes through, or maybe losses. You want to minimize the losses. C factor may be the loss factor, and then there is a generators pump in power. Consumers use the power, so there is input and exit, but also the powers need to adapt to the same thing, conservation of energy. Or it could be data in a communication network, right? So you generate data and the servers take the data. So there is again, bits hopefully don't get lost, and then as data flows through the communication links, there's a cost of using that communication link. So you see, this abstract formulation is very, very, very applicable as a network flow problem of any type of network, whether it's power system, smart grid, or not smart grid, or any communication network. And you can think of other examples as well. So let's keep the notes because it's relevant. So how do we do this? Formulate this? Actually, I have already given most of it. The decision variable is variables are the flows Xij for all Ij, right? And then the cost, the objective is minimize C. So which is sum over Ij, Cij, which is constant, which is a parameter, not a decision variable, and Xij. So that's given, right? So then let's write it a bit more formally. So I want to minimize Xij sum over ij, cij, xij, subject to, what are my constraints? First constraint is I know that my xij's should be between a lower bound and lower bound Lij and upper bound Ij, right? And this is for all Ij, for each flow. Okay, so you have a bunch of constraints. This is the box that I was talking about. So your flows are within a box. Maybe Lij is 0, so they need to be positive. Right? And then there's an upper bound, maybe Uij, you know, you melt the bandwidth constraints, or you melt the line constraints for power flow or current flow. And then the next thing is we need to just write the conservation of flow, which is if a flow enters a node, then a node should have a balance. Nothing should disappear. The flows shouldn't disappear. That means I have a Bi, maybe there's flow pumped in or minus, the B could be plus or minus, doesn't matter. And the flows that go out from I, J equals 1 to the neighbors, to all others. You know, of course, non-neighbors, the flow will be 0 in a graph. So I can actually sum it over all those that are not neighbors, Xij will be 0 automatically. And then inflows, I need to take into account inflows, all of the, again, J1 to N, Xji, those that come from my neighbors, and for those J's that are not my neighbors, Xji will be automatically 0. Right? And this whole thing should be, you know, balanced. So B can be pumped in or take it out, or you may be an intermediary node, B is 0, then your inputs should be equal to the outputs. A router shouldn't generate new data in, data out. A transformer, power in, power out. All right? And this is called a linear program, and that's it. That's it, done. So this is for all I. For each node, I can write this conservation equation. Right? This is the conservation equation. And that holds again for power and current and data, depending on how you do. So note that that's it. That's your answer. Mathematically. Look, as you've seen in the workshop, if you do this, you give it to the solver, it gives you the answer. Here you go. Practical engineering type of. If you give the wrong formulation, it will give you the wrong answer. The question here is, yeah, maybe I should make it applicable to power or comm systems. Maybe other things too. That's those two things that come to my mind. Note that it's a linear program. It's a linear optimization problem. Why? Can you think of why we call this linear optimization problem? It should be very obvious. Look at the objective function. Is it linear in the decision variables? Yes. Look at the constraint functions. Are they linear in the decision variables? Yes. That's a linear program. End of story. If you have one nonlinearity, then it's not a linear program. It's a special case of convex optimization. Linear functions are also convex automatically. So, but linear programs are easier to solve because linear things are easier to handle. Yeah. All right. Let's move forward. This is taking longer than I thought, but that's good. We shouldn't rush. Okay, second order necessary conditions. This is, again, going with the spirit of the unconstrained case, right? In the unconstrained case, we have the Hessian. What would be the counterpart? Remember, in the unconstrained case, we had the first order necessary conditions, which were taking the gradient of the objective and equating to the 0. In the constraint case, we have written the Lagrangian, written the constraints, taking the constraints into account with the Lagrange multipliers, and written the first order conditions, taking the gradient of the Lagrangian with respect to x and lambda, x being the decision vector, and then equating it to 0 to get the first order necessary conditions. Of course, the second order necessary conditions are also important. You know, first order conditions may or may not, do not tell you is it the maximum, is it the minimum. You need to look at the curvature of the objective, and together now with the constraints taken into account. So if I write the first order condition now, so this is actually, as I was saying, equal to, you know, let me write it this way. So lambda 1 gradient h1 plus lambda 2 gradient h2 dot dot dot, right? So this is this expression. All right. So you have this vector equality. That's the first order. And if you take again the derivative again, you get that matrix L at the solution x star, right? And then that matrix is actually here. The notation is a bit different, but I'm actually quite happy to expose you to different notations, because you look at a different book, you look at a different notation. If I teach you only one book, it would be very easy for me. But I find it a bit like cheating for me. I would be cheating a bit. Because if you open another book after finishing this subject, if you get confused, what have I taught you, right? So you should be able to handle different books. So in this book, obviously, the L is, this is actually the Hessian of the unconstrained case, F, and then this is the lambda, and this is the matrix that, this is the gradient matrix, counterpart of Hessian with the equality constraints. So they become then this matrix, and just like the other one, this becomes a sufficient condition when the matrix is positive definite on the tangent plane, M. So this is on the tangent plane. We look at the curvature of the combined thing, right? F and H are the Hessians of the objective functions and the constraint functions respectively. And then the second order conditions are analogous to the unconstrained case. Now, but the difference is now we have a matrix coming from the Lagrangian instead of the Hessian of the objective function, right? So this is intuitively related to the curvature, but with constraints taken into account. So this matrix is also known as bordered Hessian. If you want a technical term, there's also the being the Hessian of the Lagrangian. So it's just analogous, but you operate with the Lagrangian. That's the message to give. In the constraint case, the first and secondary order conditions are all done with the Lagrangian. The Lagrangian and Lagrange multipliers are at the heart of the whole discussion. Right? So there is yep. So just to illustrate this, we can actually, next question, again with an example, I think it's nicely illustrated. Let's keep this. Yeah, or it is relevant to this question. So we have actually, I'll actually, for the interest of time, skip the text a little bit. There is a long story here with a wireless communication example with the optimal power and bandwidth allocation in a Gaussian broadcast channel. If you have taken comms in electrical engineering, you will be familiar, but if you haven't, you can also see it as an abstract formulation. So we have the bit rate is Ri, which is determined by certain parameters like the bandwidth, and there's this beta are the constants, and then the power level. So the power level and the bandwidth together determine your bit rate in a wireless communication, which should sound reasonable to electrical engineering students, right? And then the transmission power, total transmission power over you have n receivers. then the power that you send to all of the receivers should be total power is constrained. You have a total power constraint. Of course, if I want to communicate, I use my maximum available power to get the best results. And then I have the bandwidth allocated to each channel will be the total bandwidth, right? So you see immediately some equality constraints here, right? And then the objective is to maximize the total utility. So if you have a utility function that is maybe logarithmic in Ri, that means I want to maximize Ri, but what the benefit I'm getting is tapering out, so it's a logarithmic function. So instead of trying to maximize it with all my, linearly, so the utility in R would be then something like maybe like this. So I want more and more, but after a point I start to care less and less, right? This is a law of diminishing returns. So this is a logarithmic utility. Then the question is, pose this problem as a convex optimization problem. Again, this is kind of modeling, but it also shows, we will discuss a little bit of the convexity here. Why is a convex optimization and a optimization problem? So first of all, it's about maximizing the utility. So I want to maximize over the decision. First of all, the decision variables. So I'm given the decision variables are P and W as vectors. I need to decide on my power and the bandwidth allocation. And I want to maximize my utility. So in this case, I want to show that utility of R is concave. Max P W U of R. Actually, it will be done the sum, right, over all the channels. So it will be done I equals 1 to N. UI, maybe each UI is different. This is the more general formulation of Ri with Ri given by this, right? And UI is just a concave function. So if UI is concave, convex function of a convex, actually, because this is a non-decreasing concave function, UI, then if Ri is concave, believe me when I say that the UI Ri will be also concave, and then concave plus concave will be concave functions. So this is actually, the whole thing will be a concave function. So the objective satisfies, objective is concave if Ri are concave. Because I'm taking a non-decreasing monotonic concave. UI is monotonic concave in Ri. Therefore, if Ri is concave, UI Ri will be concave. Some of the concaves will be concave. So this is a minus of the convex. Same thing we discussed for the functions. Okay. So just again, the example also exposes you to all these interesting relationships between when you combine the functions. There's a huge discussion in Boyd about this, how you combine functions and you still preserve convexity. So then what would be the constraints? The constraints will be then subject to, obviously we have the Pi equals P total, and then Wi equals W total, and then Pi Wi greater than or equal to 0 for all I, right? And that's it. So this is your convex optimization problem. These are linear constraints. If you ignore the positivity constraints, so let's say we end up with a positive result, then these will be automatically satisfied. Then you have a set of equality constraints only. Then you will have the convex maximizing concave, which is minimizing convex function. So convex optimization with linear constraints. So this will be still convex optimization. So this is concave. Let's say convex objective with mean minus, right? And linear constraints. And these constraints are also linear. Inequalities are also linear. Linear equality constraints and linear non-equality constraints. So actually, I leave it to you as an exercise. Exercise, let me write it in exercise. Check check if Hessian of objective and bordered Hessian of Lagrangian are, because we are maximizing, then they need to be negative definite, right? Remember, I always remember it from the parabolas. If the parabola's constant is negative, then it's an inverted parabola. If it's positive, then it's a bowl shaped. So they need to be then negative definite, right? Or semi-definite. Then we know that we have a unique solution, and that is the case. Or actually, if that is not the case, that you can find conditions for which that is the case. Check if, I said if, they should be, because otherwise it won't be a convex optimization problem, so they should be negative definite. Right? Okay, and I will post the solution. So it's kind of this is a nice derivative taking exercise. You can also use Mathematica if you like it as a cross check. That's what I did, to be honest, and I'll post that too. All right, so this is again half modeling, and then we discussed the Hessian and bordered Hessian. It's a kind of exemplifies what's going on there. Well, let's where we are. So this is one more example, and you know what? I might come to this maybe tomorrow. Let me skip this because I want to talk about a little bit, start discussing the inequality constraints. So question 5, remind me, we will come back. So inequality constraints, now it's time to, it's actually quite straightforward to put them into the picture once we know how to deal with the equality constraints. So it's an extension again. So now we not only have these set of equality constraints for x being here a vector again in the most general case, but now we have a set of inequality constraints. And then intersection of all those, as we discussed in the very beginning, determine our constraint set. Right? Or you can write it, this is another notation, h of x is a vector, so each of them equal to 0, then this will be the 0 vector, and then g1 to gr, you can put it in a kind of, write them in a kind of a vector-like form, and less than equal to 0, with the 0 vector. So the equality constraints always have an effect on the solution. Why? You need to always satisfy them. Right? There is no other option. Right? Is this the case for the inequality constraints? There may be cases where some of the inequality constraints may not play a role. For example, all of them, actually I brought it into the canonical form, I've written everything as less than or equal to 0. That kind of makes life easier. Even if it's greater than or equal to 0, then you can multiply the equation with -1 and make it less than or equal to 0. If there's something on the right-hand side, you can always throw it onto the left-hand side. So let's say you have some equations and you brought it to this canonical form. That's not that difficult with some algebra. Now, it may be the case that if this is x star is your solution, you may very well have the case of this. So G1 x star might be strictly less than 0. But then G2 x star and G3 x star, G2 x star might be 0, G3 x star maybe it's again less than 0. When it is less than 0, does that play a role at the solution point? I'm talking at the solution point. No, right? if I delete that equation at the solution, will that make any difference? If I delete G1 and G3, would my solution change? No, right? Because I'm inside that boundary. That boundary, I'm not hitting my nose to the boundary. That boundary is far away, it doesn't affect me. Makes sense, right? There are some constraints that are farther away at the solution. I'm at the solution because I'm hitting some boundary. In a constraint optimization, that has to be the case. There must be some boundary determining my solution. But there may be other boundaries that are not affecting me. Those constraints are called inactive. That's a very nice name. Those constraints are not active. They are not actively affecting my solution. And those constraints that are active then become equality constraints, because I need to hit the edge. For example, the box problem we were solving, that's maybe we should use that. So you are given a piece of paper of certain area. I could have said, use as much of the paper you like to create the biggest box. That would be an inequality constraint, right? So how much of the area I'm going to use? Area is less than or equal to the total area. But the problem, if I want to do the biggest box, obviously I want to use all of the paper. You see, the constraint is active, and then when the constraint is active, then it's an equality constraint. I'm not using less. I'm using exactly the whole thing. So just like what you see here. So this is active, these are inactive. So then we can define a set of active inequality constraints at a feasible point. So this is then at a feasible point, which constraints are active at that point. And if a constraint is not in the set AX, then we say that that constraint is inactive at X. So we can do this for any point, right? For any point, not only the solution, some of the constraints will be active, inequality constraints will be active, some of the inequality constraints will be inactive. Equality constraints are always active. They need to be always satisfied because they have to be satisfied with an equality. But for inequality, I can keep it as less than 0. Does this make sense? Because that's the heart of the matter with the inequality constraints. Any questions? Right? As I was saying, am I using less than the area of the box, area of the paper? Or there could be another inequality constraint like I don't know what, the color of the paper, let's say, and then the color of the paper I cannot create an example right now like with that example. We need to think about it. But you can think of some additional constraints. You can always impose some additional constraints where you don't hit the boundary of that constraint. Then those are inactive at that point. And then solution is also a point, right? So the effect of this is now the counterpart of what we did with the Lagrangian, and then writing the first order necessary conditions for the equality constraints. If we do it for the whole thing, now for the entire most general form of constraint optimization, I have still my objective function. Here I'm trying to minimize it, subject to, as we discussed before, we have these equality constraints. Now I have my inequality constraints, bunch of them, right? And suppose x star is a regular point for the constraints. I will come to this in question 6. Then there is a vector lambda, which is the Lagrangian multiplier associated with the equality part. You see this part is the same as before, right? Actually, without the constraints, this part is the same as unconstrained. Then this part is with the linear equality constraints. Now I am adding another set of Lagrangian multipliers corresponding to the inequality constraints. But if it's minimized, then I write them as plus mu, and then the gradient g. And lambda were anything, but mu has to be done, if you write it this way, has to be greater than or equal to 0. Actually, there is a way of, there is actually some nice explanation why they have to be positive. but I kind of don't have the time to go into that detail. But just inequality constraints, the Lagrange multipliers associated with the inequality constraints are always non-negative. Plus, I have this relationship, mu transpose gx star equals 0. So at that x star is a regular point for the constraint. So these are then the first order conditions, and this is called the complementary slackness condition. So what does it mean? So x star is regular if the gradient vectors of the active constraints are linearly independent. I'm going to illustrate this with the example question 6. So we'll come to this. We note that the Lagrange multipliers of inequality constraints are non-negative. Lambdas can be anything, plus minus, but mu's are, if you write it this exact right way, then mu's need to be greater than or equal to 0, each of them. And then the key point is this. The mu's actually tell you whether a constraint is active or inactive. If a constraint is positive, mu I is greater than 0 at a point x, then that constraint is active. If a constraint is 0, I'm missing the mu, right? Yeah, the sentence is wrong. If mu corresponding to the constraint is positive, then that constraint is active. If mu j of constraint j is 0, right, then that constraint is inactive. That's also not terribly obvious, but this comes from the complementary slackness condition. So if g is normally less than or equal to 0, if g is 0, then mu can be anything, can be positive. And if g is yeah, that's just actually that's not the best explanation, but just this is correct. So if the constraint is active, then the mu is positive, and if the constraint is inactive, then mu is 0. All right? Then you multiply the constraint with mu 0, you kind of ignore the constraint, in a sense, in the complementary slackness. So if the constraint is inactive and you multiply with 0, you kind of take it out of the picture, right? So there is that kind of intuition coming in. All right, so we covered quite a bit of ground, but then some things are left. I don't think I will be able to finish tomorrow unless I skip some questions. That's also possible, and giving them as homework, but that was always on my mind. But tomorrow we'll continue with some of these additional sufficiencies in the inequality case, so kind of repeating and then doing more examples and duality. Let me get this out.